All right, folks, back here with what I hope is just another quick video. Again, looking at some application of derivatives and going just a little further with functional analysis, right? As we had been developing in the last few videos is just some techniques to be able to analyze a function, to be able to determine its extreme values, right? To determine where it's increasing and decreasing, to describe its concavity. And really what we want to what we're going to see in this section of notes is we're going to go a little bit further with those extreme values. And we're going to be looking at what are called optimization problems, right? We are going to be looking at situations that are going to present a value that we're trying to optimize. That means a value that we're trying to maximize or minimize, right? Along with, depending on the problem, the potential for constraints. Our variables being subject to one or more constraints in the relationship. And what we are going to do is use our constraint relationships to take let me just go over a little lingo with you. In a optimization problem, there's what's called the objective equation, objective relationship, right? We might even say it's the objective function. Right? That's going to be subject to one or more constraint relationships, where we're going to use the constraint relationships to express our objective function in terms of one independent variable, and then use our calculus techniques, our analysis of the first and second derivative, our first and second derivative tests, to analyze for optimal behavior in that objective function. All right. There's not too much in the way of notes here, folks. It's a lot of examples, but there are some guidelines I might mention here just to begin with. You want to just make sure you read the problem closely, and what you are looking for is the function that you're trying to optimize, maximize, or minimize, the value that you're trying to optimize, maximize, or minimize, and how it might relate to some other variables in the equation, where you might also see those other variables in the equation subject to some constraints. All right? So make sure you read the problem closely and look for those items. You may have to draw a picture. That might help. That might help you organize the information that you have given in the problem, right? And you're going to have to maybe set up, based upon the information in the problem, these equations that are objective equations that we're trying to optimize, and our constraint relationships. Once we get that objective function, right, written in terms of a single variable, we can use the first derivative to find the critical values, and then depending upon initial information, how we might consider that variable behaving over some interval, we can use first and second derivative techniques to determine extreme behavior for that function, and whether or not that's going to produce a maximum or a minimum value for our function. All right. And then you can always, once you're done, you can kind of check your answer, right, when working with these problems. Here's an example, right? You can read through this one. It says, suppose you were to have 120 meters of fencing, right? And you wanted to build a pen for your animals alongside of a barn. Right? You wanted to fence in some area of space and call it a pen, right? And you want to do it next to a structure, right? The structure that we're going to call a barn. So that for one side of our pen, we can use the barn, right? The side of the barn as that side of the pen, right? And we can consider setting up the situation in this manner here, where our pen is going to be rectangular in shape, where these three sides are going to be formed with the fencing, and this fourth side is going to fall along the barn. Right? If we call the shorter sides of the pen the width, and the longer side, the side parallel to the barn, the length, right? If we want to maximize the area of ground covered by the pen, there will be a set of dimensions W and L that will maximize this area, right? That will maximize this area subject to the constraint that we only have 120 meters of fencing. Right? This is an optimization problem. Here we already kind of have the picture to help us organize our information here. Right? But what we're considering doing here is optimizing the area of this rectangular region we call the pen. And the rectangular region we call the pen is rectangular, where we know area of a rectangle is length times width. So it is just going to be the width of this pen times the length of it that is going to describe the area of the pen. And that is what we're going to try to maximize. We're going to try to get the greatest amount of area for our pen, for our animals here. Now, we do have some constraints. We only have 120 meters of fencing. So when I think about the side measurements of W, W, and L, making up the sides of our pen, the two widths and the one length, when added together, to use all of our fencing, they would all sum up to 120 meters of fencing. Right? If we were to use all of our fencing in order to optimize the area, well, we would use 120 meters of fencing. So W plus W, the two widths plus the L, must all add up to 120, or 2W plus L must equal 120. And that's going to present ourselves with some constraints. So if we bring these into picture, right, this is an optimization problem where we're trying to optimize area. We're trying to optimize this value we calculate as L times W. This is subject to some constraints about perimeter of our pen, which is given by length plus 2 times W. Right? We know that that has to equal 120. And under that constraint, where our perimeter is equal to 120 meters, or L plus 2W must equal 120, I can solve for L, and that will imply that L is equal to 120 minus 2W. And with 120 minus 2W for L, I can actually substitute it into the relationship here for, well, careful there, not there, up here, into our relationship for area, and I can think about our area being 120 minus 2W times W. Or what would be 120 W minus 2W squared. Right? This being what we might note now is a function of W. Right? The area of our pen can be described by this function of W, a function of just the width, because we know our length related to our width has to be 120 minus 2W. Now that we have our area expressed as a function of just the very W, we can look for the width that is going to optimize that function, that's going to maximize that function. And where we might find that width is at a critical point for this function, right? If we note the first derivative of this function is going to be 120 minus 4W. That does exist everywhere, where our only critical point will come when we set it equal to 0 and we find a width of 30. 30, a width of 30 should give us a maximum area for our pen. How I can double check that it is a maximum is I could consider running the second derivative test on that value of W30, W equal to 30. The second derivative of my function, you'll notice, is simply -4. The derivative of 120 minus 4W is just the value -4, which is always negative, which means this function area here, described here in terms of width, is always concave down. And if it's always concave down, that means at the top of that concavity, there must be a maximum value, a local maximum in this case, right? We know from the second derivative test, right? So yeah, it does appear that this width of 30 would allow us to find a maximum area for our pen, right? Ooh. Indicating, right, again, we note here that A double prime at 30 is equal to -4 is less than 0, so A of W is concave down at W equal to 30, meaning at W equal to 30 meters, a maximum value for area is occurring. Right? And we should probably point out what is that maximum value for area. Oh, let's do that at the end here. Thus, when W equals 30 meters, using our relationship with L, we can then say the length is going to be 120 minus 2 times W. It's going to be 120 minus 2 times 30, which is going to leave us with a length of 60 meters. Right? And the area of the pen next to the barn will be maximized, right? The area of the, okay. Thus, when W equals 30 meters, implying L equals 60 meters, the area of the pen next to the barn will, let's say it this way, will have a maximum area of A equal to 60 times 30, right? Length times width, which would equal, what is that? 1,800 meters squared, right? This would give us a pen with a maximum area of 1,800 meters squared. If we tried any other dimension, right, with the 120 meters of fencing, our area would always be less than 1,800 meters squared. When the width, all right, the width being the side perpendicular to the barn is 30 meters and the length next to the barn is 60 meters, that will form a pen of 1,800 meters with a maximum volume, or not volume, area, right? My apologies. A maximum area there. That's an optimization problem. It's a word problem. It's a word problem where we are going to have to develop what we call our objective function, a function where we are trying to optimize its value, right? Minimize or maximize it, that value, where that will often involve more than one variable, where we might have to introduce some constraints on our variables in order to see that optimization. Otherwise, if we had unlimited fence, we could build an unlimited sized pen, right? If we had unlimited amount of fencing, right, we could buy, or we had the funds and the resources to produce an unlimited amount of fencing, that pen could be as big as we want it to be, right? It's not until we introduce that we're limited in the amount of fencing that we have, 120 meters, is that when we have the situation for an optimization problem to develop. So the constraints are part of the problem, right? They introduce themselves as part of the problem. Here's another example. Here we consider minimizing, right? Maybe we have to paint this three-dimensional object, and we want to minimize how much space we have to paint, right? That'll minimize the amount of paint we have to paint with, and that'll minimize the amount of time we have to spend painting, right? And here we're considering minimizing the outer surface area of a cylindrical tank that must still hold a particular amount of a, let's say, fluid here, right? Volume, 1,000 cubic meters, right? Maybe this is a transportation tank, where we maybe transport something like milk, right? Or fresh water, where that tank is supposed to hold 1,000 cubic meters of milk or water, right? But needs to be cleaned, right? And you don't want to have a tank that's too big to clean, right? Or where the surface area gets really large and it takes a lot of cleaning equipment and a lot of time to clean that surface area, right? So this becomes an optimization problem, right? I think here, consider minimizing this outer surface area of this cylinder if the entire volume within the cylinder must be 1,000 cubic meters. What we're trying to minimize is surface area, where surface area is going to become our objective function. Now, it is a two-variable function. It depends upon both height and radius for the dimensions of the cylinder, the height of the cylinder and the radius of its circular base. If we think about a formula for that, well, the area of the two circular bases, the top and the bottom of the cylinder, those are circles. They have an area given by pi r squared. Pi r squared for the top, pi r squared for the bottom circle. So there's two of them, so our formula would start off 2 pi r squared for the two circular bases. Now the lateral side around that forms the side of the cylinder, right? The cylindrical shape itself is formed by what we would note if we were to actually take that lateral side and unwrap it and fold it out into two-dimensional space. It actually takes on the shape of a rectangle. A rectangle whose height is h and whose length is the perimeter around the circular base. And what's the perimeter around the circular base of radius r? Well, that's what? 2 pi r. Right? So the area of this lateral edge, being circumference times the height, would be 2 pi r times our height, h. And that gives us a surface area formula that we see following here. Right? In this case, we want to optimize this surface area formula seen here. This 2 pi r squared is the area for the two circular bases, and the lateral side is the circumference of the circle, 2 pi r, times our height. And what we end up with is a description of surface area that depends upon both the radius and the height of our cylinder. Now, this is the objective function, but it's two variable. It involves both r and h. And we are subject to some constraint where we might be able to use some of that constraint to develop a relationship between h and r that we can use to express this objective function in terms of just one variable. And that constraint is the fact that the tank must hold 1,000 cubic meters. All right. Otherwise, if we're trying to minimize the surface area, we just shrink it down to the point where it's really not going to be a tank at all. Right? We have to have some constraint on how far we're actually physically allowed to shrink it down. And that is given by the volume of the tank. All right. So if we think about volume, notice volume of a cylinder. What is the area of the base times the height? That's pi r squared times h. And that is subject to the constraint that has to be equal to 1,000 cubic meters. So pi r squared times h must equal 1,000 cubic meters. And if I solve that for h, that means 1,000 divided by pi r squared is equivalent to the value of h. And I can substitute that into my relationship here for the surface area for h and obtain just a function of r. And here becomes my objective function, s of r. Surface area for this cylinder based upon just the radius of the cylinder. It is the area of the two bases based upon radius added to the area of the lateral edge, which is now also expressed in terms of just the radius. Substituting in for h, this quantity 1,000 over pi r squared, which does simplify. The two pi's will cancel, and one of the r's in the numerator will cancel with one of the r's in the denominator, moving it to the denominator. And we can think of s of r being this equation seen here, this variation of a rational function. If we think about finding the derivative of that rational function, right? In the current form, we could just apply the derivative operator using a little sum and difference rule, constant multiple rule, and power rule, and end up with 4 pi r minus 2,000 r to the negative second power, interpreting this r in the denominator as r to the negative first power. Where if I express this now with a common denominator, this will actually express itself as 4 pi r cubed minus 2,000 over r squared in value. Right? With that common denominator of r squared. Now this rational form, s prime, does not exist when r equals 0. So 0 is going to become our first critical point, and it actually equals 0, right, when the numerator is equal to 0. So setting the numerator equal to 0 and solving for this r, we're going to see it's going to be the cube root of 2,000 divided by 4 pi. Right? Well, the 2,000 divided by 4 simplifies to 500, so this becomes the cube root of 500 divided by pi. And that is our other critical point. And what we might begin to try to argue there is, yeah, that other critical point, right? Not the critical point of a radius of 0. That will not produce a cylinder for us. But this critical point here has a lot of potential for being a minimum. It might be the minimum value. We could take a big leap to say that it is, where we will expect to see the minimum value in our surface area. But just to double check it, I do think I run a second derivative test here. Ooh, I don't test it. All right, it can be likely assumed that that is going to be the radius that produces the minimum surface area, with our height being equivalent then to 1,000 divided by that pi r squared, substituting in for that value. If we were to judge it, let's put in a judgment. Without the second derivative here, we could put in a judgment with the first derivative. All right. If we notice in the first derivative, the denominator is always positive. It's the numerator that can fluctuate between being positive and negative. Now, when is it going to be positive or negative? Well, that's going to be on either side of this critical point. Now, that critical point is the cube root of 500. So that's a, what? That's a, somewhere, I think, around 20 or so, divided by the cube root of pi. So it's, I believe, not terribly big. I do approximate it down below. Let's bring our final answer in here. Yeah, I do find that it is approximately 5.4 meters. All right. One thing we will maybe point out here just for the moment. Oh, I don't want that underneath there. We'll say that's approximately 5.4 in value. And we can test that 5.4. We can think about being a number smaller than 5.4, substituting its value into here. All right? Like, for instance, 5. Or we could go real small. Let's go with 1. All right? If we had a radius of 1, this would be just 4 pi. 4 pi minus 2,000. Now, 4 pi is, what, 13 something. So minus 2,000, that would be negative. We would be increasing before this value at 5.4. All right. So we're increasing before it. What about after it? What if I pick a large number like 10? Well, I know 10 cubed, right, is 10 times 10 is 100 times another 10 is 1,000. And if I take that times 4 pi, I have 4,000 pi, which is a little over 12,000, 13,000, somewhere in there. Where if I subtract 2,000 from that, that's still going to leave me at a positive value. So if I'm positive, sorry, let's back up here. That's going to leave me with a positive value, so that means I'm increasing after this location. And, hold on 2 seconds, folks. All right, sorry, folks. My wife was calling, asking for my dinner order. Didn't want to miss that call. So, back here just real quick. Again, I just screwed up my analysis, right? I had just said when we are less than 5.4, if we're 1, we're actually going to be a negative, which means we're decreasing. We're decreasing before this point. And if we're a number larger than 5.4, like 10, right, we would be positive, close to 10,000. And we would be increasing after this point. So if we're decreasing before this point and increasing after this point, then we must be, what? A local minimum value. So yeah, our assumption that we have a minimum there is a good assumption. Right? We've just supported that with the first derivative test. So maybe I should say that here. So r equal to 0 and r equal are critical points, and it can likely be assumed that r equal to this is a radius producing the minimum surface area. And we'll say here, this can be confirmed. We just did it with the first derivative test, where f prime of x is less than that cube root of the radical given by this. Ooh, I should be careful there. Is less than 0 when our radius is less than that, right? And f prime of x is greater than 0. Right. When we see the following behavior, I don't need that comma there. I'm going to grab this just for the quickness and go over and change this sign, right? When our radius is greater than this quantity, right? That will be starting to confirm the first derivative test for us here. This can be confirmed when the first derivative test, where f prime of x is less than 0 when r is less than this value, and f prime of x is greater than 0 when r is greater than this value, right? Maybe we should say here indicating, and I got to go back and change one other thing here. We're indicating here, we're not actually talking s prime, we're talking s prime. All right, is what? Increasing, right? Is increasing as r increases through this critical point. Let's say it that way. And this is not f prime. This is, again, we're talking s prime. All right. Is less than 0, and it's not at x. I was going general with that definition. We're looking at it at r here. All right. So let's make those quick little corrections in the notes and give ourselves a little confirmation on that local minimum value. All right. This is optimization problems, folks. All right. They involve an objective function. Here, our objective function was the surface area. All right. And its description, right, relative to the variables r and h. This is what we were trying to minimize, right, in our problem. That's our objective function. And to be able to work with minimizing it, we do have to write it in terms of one variable where some constraint will certainly come in handy. And in an objective function, or in optimization problems, you're going to be subject to a constraint. That's what causes the optimization to have to occur. Right? So with the constraint, you can usually, if you're given enough information, right, be able to rewrite your objective function in terms of just one variable. And then using derivative techniques, first and second derivative tests, right, be able to determine your critical point and test your critical points for extreme behavior. And I did that here now in 2 examples. I used the first derivative or second derivative test in my first example and the first derivative test here in my second, just to avoid having to find the second derivative, this second example around. These are optimization problems, folks. You're going to want to just practice, right? I can't do every single one of them for you here, but I did do a case for a maximum, and I did do a case for a minimum here. And I did try to illustrate a little bit of complexity in their calculations. All right. But that does kind of wrap functional analysis and some of the application we're going to spend our time with. Where we're heading, I think we're going to talk L'Hopital's. We're going to start to look at L'Hopital's rule and its application. All right. And there is some other application in there. We're getting a little short in time for class. I probably will still write it up. I might even still post videos on it. We got to talk linear approximations and get into Newton's method. I would love to be able to do that. It is a bit of an optional topic for us in our schedule. We do have to also talk mean value theorem and get into antiderivatives and begin chapter 5, or begin our, I should say here, not to date this video, our discussion of just integration. All right. So with that said, I am going to end my video here, and I will see you in the next one.